Thames, from the first Roman trading settlement of Londinium to the fabulous city of nearly 10 million people, home of the mother of parliaments and worldwide trading and commercial centre. In Greater London, more than 20 bridges carry millions every day. In a way, they resemble the spokes of a wheel of fortune. For more than 2,000 years, the Thames has made London, and London has made the Thames. The two are indivisible, yet together they provide jobs, homes, and security for millions, and likewise provide the stuff of which our history is made. And yet, whether carrying ships out to the wide beyond or guiding them back to port, the Thames and its Londoners have from time to time, and with increasing violence, suffered the assaults of the very seas which it serves. This was the last and worst of the tidal surge floods that have struck with deadly menace over the centuries. In 1953, here in the Thames estuary on Canvey Island alone, more than 300 people lost their lives. Each succeeding generation has suffered worse flood disasters along the Thames. This is due to a combination of two main phenomena, with the effects of which the engineers are battling and are now within sight of victory. One of these is our weather system. The other is an aftermath of the last ice age. Let us look at these briefly. The phrase, "a trough of low pressure moving in from the Atlantic," is depressingly familiar. Such a depression raises up an enormous volume of water and brings it towards the British Isles and northwestern Europe. When such a system rounds the north of our islands and turns southwards, it pours this mass of water into the narrower and shallower North Sea. In the 1953 flood, nearly 500,000 million cubic meters poured into the North Sea, raising the mean level by 2/3 of a meter. But as the surge storm conditions and gale force winds developed, the southern half of the North Sea below the Humber rose by 2 meters, and off the Dutch coast by over 3 meters. In such conditions, the funnel-like character of the Thames estuary turns the Thames into a destruction route, with life and property the victims. The weather is superimposed on the effects of the last ice age. This covered Britain north of Thames and Severn. Northwest Scotland must have resembled the Greenland ice cap. Relief from the crushing weight of ice is still being recorded. Post-glacial recovery may take all of 15,000 years, and northwest Scotland is still rising by 4 millimeters a year. By contrast, eastern Britain from the Forth to below the Thames has been subsiding. Ancient forests and river courses now lie 30 meters below the North Sea. For Londoners, this means that since the Thames took on roughly its present shape and course, mean tidal levels in London have been rising by nearly 2/3 of a meter every 100 years. The earliest known London bridge over the Thames was built by the Romans in the 1st century AD. It was a wooden structure founded on driven timber piles and comprising a deck system overlying a series of struts, giving it some 36 spans. Some could be pulled open like mini drawbridges for larger craft to pass through. The bridge also acted as a crude flood barrier, preventing the flooding of the marshes we now know as Southwark and Lambeth. Some idea of the effect of rising mean tidal level can be illustrated diagrammatically. The first London bridge would today be deep underwater. Had the barrier not been built, then a surge flood of the 1953 level would today overwhelm us. The damage to London would be incalculable. Below us, in that great curve of the river, is the bulge which until recently was the Surrey Docks, currently being redeveloped. The whole of that would be completely submerged. Standing upon Westminster Bridge, even Wordsworth might be lost for words. The Bank of England, old lady of Threadneedle Street, might face unheard-of problems of liquidity. Worst of all, 500,000 London homes below the Trinity high water level would become a disaster area of frightful magnitude. That nightmare is now in the past. But below is the Thames barrier at an early stage of work, some 7 years before completion. And it is the highlights of the 7-year battle that we are now about to see. From here to victory. In the beginning was an artist's impression to give Londoners some idea of what the finished product would look like. The barrier had to satisfy 3 musts laid down by the GLC. 1, reliability in operation. 2, Thames to remain navigable. 3, aesthetically acceptable. To face the challenge of the Thames barrier, it was natural that Davy McKee, world leader in heavy engineering, and Cleveland Bridge, world leader in steel construction, should come together to form the Davy Cleveland Barrier Consortium. Thus the elegant design of consulting engineers Rendell, Palmer and Tritton and GLC architects could be brought to triumphant reality. The principles, as seen on this model, are fairly simple. If only everything about the barrier were as simple as it looks here. Each of these concrete piers houses a control room, although the control building on the Woolwich Bank will operate all spans at once. The rising sector gates lie in massive concrete sills, which have sections of the underground service tunnels incorporated in the precast structures. The flat side of the gates lie flush with the riverbed. Before any installation of the gates or gate arms could take place, the sills were towed out, positioned, and sunk between the piers. Providing the operating machinery has been the responsibility of Davy McKee at their Sheffield works. Here, for example, one of 9 trunnion support structures is being assembled. With its mating shaft, it will eventually become the main gate arm pivot point. The first of the TSSs, as they were familiarly called, is here being installed deep in its appropriate pier at the barrier site. That was 5 or 6 years ago, and neither it nor the other TSSs will be seen again. They support the gate arms, as will become apparent later. While this was going on, 32 massive hydraulic cylinders were being assembled in the Davy workshops, ready for Cleveland to install. There on the model, slightly larger there on the barrier. Another piece of the jigsaw for each gate is this shift and latch mechanism, being trial assembled in the shops before journeying down to the Thames. It is used to inch the gate round for critical parts of the rotation and lock it in its various operating positions. In emergencies, it can be used in place of the rocking beams to raise the gate entirely on its own. In that sense, it may be referred to as a fail-safe mechanism. Like all the working parts of the barrier, it gets a tough workout on site before satisfying the consortium's engineers. The gates, arms and rocking beams were built not on the Thames, but 200 miles north at Cleveland's Port Clarence works on the River Tees. Here are facilities for both building and loading out large structures for the rest of the world, especially offshore oil and gas structures in the North Sea, as well as these massive structures for keeping the North Sea out of London. Building the main elements of the Thames barrier here occupied Cleveland for several years. Looked at from ground level, these gate arms in various stages of construction might well pass as a series of park bandstands. They've been described at design stage as hollow steel discs, a typical engineering understatement. Each contains several hundred tons of kentledge to act as counterweights during rotation of the gates. The gates, they call them gate leaves when separate from their gate arms, are a triumph of fabrication. To maintain the shape and very tight flatness tolerances, levels were constantly checked by laser equipment. The segment of a circle in cross-section is maintained throughout the length of double skin, if skin is the right word for 40 and 50 millimeter thick steel plate. Welding operations seen here are for the internal web plates and diaphragms, which will support the curved shape and provide a means of distributing the load. By this time, an air of expectancy is growing on both Tees and Thames as the date for the first major movement and installation draws near. The very considerable amount of work by the diving teams to check underwater arrangements are carried out in almost total blackout conditions. Down in the primeval soup of the Thames, all is positioned by sense of touch, for nothing can be seen. If it could, we would have filmed it. At last, the first major move is about to be made. One of the large gate arms for the first of the 61-meter gates. This method of moving large structures and loading out has since become almost standard at Port Clarence. Several hundred wheels, each with independent suspension and control, and powered by tractors with a combined output of about 2,000 horsepower. Tugs maneuver the pontoon barge to its end-on position at the quay. Ballasting and deballasting are carried out to fit in with the tidal timetables, for there could be a difference of over 5 meters between ebb and flow on Tees. The last gap between land and water is closed by the ramps being lowered somewhat like ancient drawbridges. For several weeks prior to this moment, work is being carried out aboard the pontoon to install various sea fastenings, for once at sea, nothing except men must be allowed to move about. Winches aboard the pontoon barge pull while the tractors now add their weight in pushing from the rear. They can also act as emergency brakes, should the load change its mind and go into reverse. Center of gravity is carefully maintained as the load moves smoothly onto the barge. This is a big moment for Cleveland and for Port Clarence, for after several years of work, the first major structural component of the Thames barrier has been loaded successfully. All that remains is to tow the gate arm down to the Thames, there pick it up and install it in the right place, give or take half a millimeter. Night time belongs to the tugmen, and for the next 36 hours, so too does the fate of the Thames barrier. At the barrier site, Cleveland's engineers, erectors, boatmen, movement controllers on land and water are all ready and waiting. So too are the men who maneuver the two Hebes, giant floating cranes among the biggest in the world. One of their great attributes is their ability to work in tandem and move together, literally to within millimeters. As they upend the 1,200 tons of steel gate arm, they might be dancing a pas de deux in some water valley. A gate arm that is half a degree out of correct alignment could cause several months' delay for corrective measures. It has got to be right, and in many respects the installation of the gate arms is the most critical factor in the whole cycle of barrier installations. There seem as many divers as some South Sea Island pearl diving complex, but conditions could hardly be different. Everything underwater has to be checked, monitored, and reported upon immediately. The detailed work, though not as spectacular as the big stuff, does involve a mechanical engineering force which accounts for well over half the total site force. Cleveland's site management controls as much or more mechanical engineering as it does civil and structural engineering. And throughout, the Thames remains navigable. The Royal Yacht Britannia has no problem clearing the 61-meter or 200-foot span between piers. With one pontoon barge down on the Thames, another is preparing to receive the first of the large gate leaves at Port Clarence, where it has been assembled. Load-out procedures are similar, but the trailer is longer. Yet another strange cargo passes beneath the transporter bridge engineered at the beginning of this century by Cleveland. The bridge may itself become a piece of industrial archaeology before it sees a more vital load than the Thames barrier passing beneath it. Sail away is calm enough, but by the time we meet up again with this particular gateleaf known as Gateleaf C, we shall find ourselves in a seemingly totally different climate and environment. Memories are often unreliable. This was a Sunday night in mid-December 1981. The records will show it to have been the coldest mid-December for half a century. A blizzard blowing along the Thames has closed every main road for some 50 miles all around. But the program has reached a critical stage, and a courageous decision was made by Cleveland's site management. Lift, move, and install Gateleaf C, the first of the 4 navigation span gates. The 2 Hebes are ready, and the lifting beam has been attached to Gateleaf C. Suddenly, the weather changed dramatically. Within minutes, temperature shot up and the snow turned to pouring rain. Halfway through lifting, the snow practically avalanched off the Gateleaf. Having lifted the Gateleaf several meters above water, the Hebes now await tidal movement several hours later. The PLA, Port of London Authority, had tracked the path of the storm which gave us last night's blizzards, and advised that at this very moment the eye of the storm would pass over the site, giving us 2 or more hours of sunshine and calm. And so it transpires. Anyway, the Gateleaf is on the move upriver to the piers, to the position it will occupy for the rest of its life. In a way, the work of the past several years have been leading up to this moment. And with its success, the men of the Davy Cleveland Consortium, or DCBC as it is known down Woolwich Way, have managed to get a nose in front. From this moment, only about 11 months remain for Cleveland to complete the contract on time and hand over the barrier in working order. DCBC is not now going to lose that narrow lead, whatever problems and distractions the future may hold. The Gateleaf is finally down. At this stage, the Gateleaf sits on top of the gate arms, spanning the piers like a bridge, a position it will only resemble in future when raised 180 degrees to the maintenance position. By the spring, it and other gates lie in their sills, with the flat side flush with the riverbed. Now the different bits and pieces of machinery, cylinders, rocking beams, shift and latch mechanisms, all make more sense. Each pier has its own power pack and several kilometers of pipework, and might well be thought to comprise a ship's engine room. Testing time. Water bubbles and boils as the gate comes up, not unlike a great whale from the deeps. Its special protective coating has also passed its first test. One end of the gate is rigidly fixed to the arm to prevent sway. This is called the fixed end. The other end is connected to the arm via a series of 13 hinges. Not exactly door hinges, for they weigh some 3 tons each. The hinged end allows the gate to rotate. With the aid of a special bearing used to mount the gates on their pivots, end thrust towards the piers is virtually eliminated should the gate become deflected under load. Differential water level here is about 3 meters. It could at critical periods be 3 times as great. The gates are now at their flood protection position of around 90 degrees. The curved skin provides separation between differing water levels. The center of radius of the curve coincides with the center of rotation of the entire structure. All loading is resolved into one resultant force passing through the center. As powerful hydrostatic and other forces build up with the tide, equilibrium is maintained at all times. There is a gap between sill recess and face of gate to enable a high-velocity jetting or scouring action of the water to clear any debris from the sills prior to returning the gates to their riverbed position. This will prevent jamming when lowered again. In surge flood conditions, the gate can be moved another few degrees by the shift and latch mechanism to enable a controlled upstream flow beneath the gates. This will prevent the possible build-up of a return or reflected wave traveling back downstream. The Thames and the alien waters from the North Sea and the Atlantic will thus be kept under control. The job is completed. Target date met and the barrier handed over to the Greater London Council. It has been one more test for Cleveland Bridge and Davy McKee. The result is a triumph of engineering. Since long before the legendary Noah, floods have formed part of man's life on our planet. A few have been beneficial, as in the Nile Valley, but most have been unmitigated disasters. The barrier has shown that man, engineering man, can meet and defeat the challenge. All credit to the workforce of welders, erectors, divers, watermen and craftsmen who, led by the engineers, have won a victory over the elements. In a world of uncertain values and problems, British engineering stands out preeminent, a ray of hope for the world of tomorrow.